So chapter 8 discussion questions, page 174, starting with number 2, which is going to Erica. All right, so number 2, we have this interesting looking picture at the bottom there. It says the figure shows one direct path and 4 indirect paths from point I to point F. Along the direct path and 3 of the indirect paths, only a conservative force acts on a certain particle. Along the 4th indirect path, both a conservative and non-conservative force act on the particle. The work in joules done on a particle going from I to F is indicated along each straight line segment of the indirect paths. A, how much work is done on the particle in moving from I to F along the direct path, which isn't written, but they're giving us all the segments. Let's just add them all up to start. So here's I, here's F. We could have gone way out here. We could have gone right, and you had the path, and we could have gone low and even lower. All right, something like that. What is the work done on the top path add up to? Like the blue. Sorry, the blue. 12. Okay, 12. So 12 joules of work is done from I to F that way. How about the one below it? The pink. Yep. 1. How about the purple? 12. And the bottom one. Or?
Hold on. 10, sorry. 12.
All right. Add the 2. Okay. So which one of these is not like the other?
The negative 1.
The negative 1. So the negative 1 must be where there's also a non-conservative force acting. So if it tells you that 4 of the paths are conservative and 1 is not, must be the missing path. Also 12. Okay. So that's part A. How much work is done on the particle along a direct path? Well, it's got to also be 12 if they said that 4 were conservative and 1 was not.
Why are you adding different work?
Pardon?
Why are you adding different work?
Because those are the works done in each little segment. We're just finding the net work. Oh, yeah, no. Last part, how much work is done by non-conservative force along that path? So we figured out it's this. Maybe. We got to read carefully, because you often have to read the question carefully. Is it talking about the work done by one force, or is it talking about the net work? And it said, along the 4th indirect path, both the conservative force and the non-conservative force act on the particle. So this is the net work. And what did we know was the work? Yeah. So this was from the force plus force unconservative, dot D, whatever. But the net was negative 1. So what must be known conservative work done? Negative 13. So that's the work done by the non-conservative. Does that make sense? Just read it carefully. It was telling you that this was the sum of conservative and non-conservative. So that's the net. The conservative was 12. Okay. Next. Number 3, west. We have our favorite spring. Spring is stretched by 3 centimeters from its relaxed length. Here are 4 choices. The initial stretch is changed to either a stretch of 2, a compression of 2, a compression of 4, or a stretch of 4. Rank them according to the change in elastic potential energy. So we're finding change, and we're assuming the U initial would be calculated how?
1/2 kx squared.
Good. Which in the x was, 3 centimeters squared. So if you're simply finding the change in most positive first to most negative last, which situation here with this new potential energy would give you the most positive value if we plugged it? Be the same then? Yeah, and then A and B. Because you're squaring it, so it does not matter if it's positive. All right, good. All right, Daniel, we're going to skip over to number 6. Some of those are kind of similar. All right, so Daniel, number 6 says that the picture on the top of the next page shows 3 plums. Why plums? I don't know. But they are launched from the same level with the same speed. One moves straight upward. One is launched at a small angle to the vertical, and one is launched along a frictionless incline. Rank the plums according to their speed when they reach the level of the dashed line greatest first. And they're all launched with the same speed. But what would be true about them when they get to the dashed line? Is the incline frictionless, or does it have friction?
It doesn't.
It doesn't, okay. So there's no non-conservative force acting there. Just think about conservation of energy. What type of energy do they start with? Kinetic. They're starting at ground level. They just have kinetic initially. And they all have the same initial kinetic. Now when they get to the dashed line, and yeah, it'll take some of them longer to get there, but when they get there to the dashed line, what would be true about their potential energies? They're the same. So what's got to be true about their kinetic energies at that line? They're the same. That's the only way we would have conservation of mechanical energy there. They'd all have to have the same speed. All right, and then similar to number 7, kind of, Tyler, number 7. The picture below shows a horizontally moving block, and it can take 3 frictionless routes, differing in elevation, to reach the dashed finish line. Rank the routes according to the speed of the block at the finish line. So what do you think there? Do they all have the same? Okay, now compare your dash line to Daniel's dash line. His is a horizontal line, yours is a vertical line. So do they all end up at the same height? No. So which one's got to be going faster? 3. Because it's going to have less what type of energy? Potential, so more of it's got to be kinetic. All right, 3, then 2, then 1. Okay, and then what about travel time? Which one's going to take the longest time to get there? Yeah, probably 1. And then 2, and then 3. Okay, so same idea with conservation of energy. Back to Daniel's question, again, do not confuse that question with like the speed as to which one gets there first. Obviously 1 would get there first. It's taking the most direct path there. But just because it gets there first, we're talking about the velocity when all of the objects are there. All right, next one, number 9. Brandon. All right, picture below shows 2 arrangements of the same 2 blocks on a frictionless plane. The blocks are connected with a taut cord that runs over a massless, frictionless pulley. In each arrangement, the hanging block descends when the blocks are released. Consider the total kinetic energy of the two blocks when the block has descended by a certain distance d. So in either case, they're dropping distance d. Is the total kinetic energy in arrangement A more than, less than, or the same as that in B? In this case, no. Because there's two objects to consider here. It's not just Tyler Daniels' question where we're talking about one object. We've got to consider both of them. So you got this one, and you got this. Okay, and we have the flat. Okay, so we're saying they both drop the same distance. So what is true about the change in potential energy of these two blocks from going from here to here? They're the same. Starting the same height, going the same height. What about the change in potential energy of these two blocks? Are those the same?
I guess the other one's higher.
Okay, so it starts out with more potential. Does its potential energy change as this goes down? It's still this whatever height above ground level. It's staying at this height above ground level. But what about this? This system here, as the blocks fall, well, yes, these blocks are losing potential energy, but that's the same. This block here is gaining some potential energy. So this system here is gaining more potential energy. So if it's gaining that type of energy, what would have to be true about its kinetic energy compared to this one? It would have to be losing it. And maybe you can imagine this if you actually set this up. I mean, which one's going to slide faster? This one. Okay, this one's going to go a little slower. It's going to have less kinetic energy by the time it gets down here because some of that energy has been transformed into more potential for this block. Does that make sense? Still trying to say energy is conserved, but this particular block here is gaining potential. So the whole system, in order to be balanced, must be losing kinetic. Not necessarily losing kinetic, but has less kinetic than this situation. Okay. Number 10, Thomas. All right, 3 more. This one's just kind of semantics, paying attention to the wording here. All right, number 10, you have an initially stationary block is released at time t1, and it's going to slide down a frictionless ramp to a massless spring, which it reaches at time t2, then compresses until the maximum compression is reached at time t3, which means it will be stopped at t3. So from t1 to t3, what happens to A, the kinetic energy of the block? And I'd like to just break it into t1 to t2 to t3. So from t1, where it's starting, to t2, where it just hits that spring, what happened to the kinetic energy? It increased. What happens from t2 to t3? It's going faster into that spring? Yeah, once it hits the spring, it's going to be slowing down. All right, part B, the gravitational potential energy of the block Earth system. So from T1 to T2, what's happening to potential energy? It's decreasing, it's getting lower. And then how about from T2, where it hits the spring, to T3, where it stops? What's happening to the potential energy? Gravitational potential energy. Is it going back up?
No, but it's slowing down.
Okay, so
The first one, the kinetic.
a different type is increasing. The first,
If the kinetic went down, does the potential have to go up?
the whole potential, yes. But it's only specifically saying the gravitational potential.
The kinetic is going down.
Yeah, it's still going down, so the height's less, so still less. All right, now the other question. The elastic potential energy of the spring. I mean, what is that from T1 to T2? Good, is nothing. What about from T2 to T3? What's happening? Now it's increasing. Okay. All right, and then D. Actually, I want to skip to F first because that's what you're going to think of first, probably. The mechanical energy of the block, earth, spring system. What is happening to the mechanical energy of everything from T1 to T2? Staying the same. Good. That's the always stays the same, always conserved. So F, it's always the same. Doesn't matter what we're talking about. All right, but D says the mechanical energy of the block, earth, system. So that's ignoring the spring, the mechanical energy of the block, earth, system. So from T1 to T2, what would we say about the mechanical energy of the block, earth, system? Has it hit the spring yet? Okay, so spring's irrelevant. So this is the only two types of energy are potential and gravitational potential and kinetic. So they're both changing, but is mechanical energy lost there? No. So the mechanical energy of the block earth system, that's constant from time 1 to time 2. But I guess if you just didn't know the spring was there, what would you say seems to be happening to the mechanical energy of the block earth system when it hits the spring? Yeah, it would seem like it's decreasing because it's slowing down for no apparent reason. Why would we be losing all this kinetic energy? Well, of course, we're losing it because of the spring, but it said ignore the spring for a second. All right, and lastly, E, the mechanical energy of the spring. So what is the mechanical energy of the spring from T1 to T2? Is the spring involved from T1 to T2? So nothing. Okay, so it starts out as nothing. But then what is happening to the potential energy of the spring after the block hits it? Increasing. Okay, so just watch the wording there. I think the most important part is F. The mechanical energy of the entire system is the same. It's conserved. All right, 2 more. Emily, 12. Okay, so we have a potential energy graph below. It says rank the regions, either A to B, B to C, C to D, or D to E, so stopping at E, according to the magnitude of the force on the particle greatest first. And again, I use the word magnitude, so that means what doesn't matter?
The positive.
Positive or negative doesn't matter. So.
The greatest would be A to B,
Mm-hmm.
and then C to D,
Mm-hmm.
and then B to E and B to C.
Perfect. Okay, so you're just looking at the slope. Okay, what value must the energy E of the particle not exceed if the particle is to be trapped in the potential well to the left? And I know we haven't talked about that terminology, but maybe you can figure it out. And almost imagine that graph actually is a roller coaster. You're a cart on a roller coaster. There's nothing powering you. You're just released from some high point, and you're on these curves. If you're going to be trapped in the well from, where did it say? Okay, the well at the left. Then what must your energy not exceed? 5. You can have a maximum potential energy of 5 and still be in that well, but as soon as you have more energy than that, it would have to be kinetic, and so you'd have to be moving out of that well. All right, C, how about to be trapped in the potential well to the right? On the right end, what about the left end?
Oh. So what
It goes up to 6, yeah, the dip.
Okay, so it's the one on the right.
So on the right end, it does go up to 6. But what about
If you have 5, you go off.
Yeah, if you were more than 5, you could go back the other way. Okay, so still 5. D. What value of the of the energy must the particle not exceed to be able to move between the two potential wells, but not to the right of point H? Okay, so that's can't exceed 6. And then for what situation in those regions will the particle have the greatest kinetic energy? Good, because that's the lowest potential. And so how about the least speed? Good, D to E. It's going to have the least speed where it has the most potential. All right, and last but not least, Zach. Number 13. That's an easy one. Okay, so in the picture below, a block slides from A to C along a frictionless ramp and then passes through horizontal region C to D, where a frictional force acts on it. Is the block's kinetic energy increasing, decreasing, or constant in region, well, starting with A to B? From A to B, what would you say about the kinetic energy? Increasing. B to C. Decreasing. And C to D. Well, read it. It said a frictional force acts there. Then it's decreasing. All right, and then D, is the block's mechanical energy increasing, decreasing, or constant in those regions? So back to A to B, what would you say? Mechanical energy.
Mechanical energy?
Yep. Mechanical energy doesn't just mean kinetic, it doesn't just mean potential, it means the sum of the two. So of course, while one goes up, the other goes down. So it should be constant from A to B. How about B to C? Also constant. But what about C to D? Is the frictional force, well, without the frictional force, what would you have said happens to the kinetic energy from C to D? Stays the same, but with the frictional force, it decreases. Yeah, the kinetic decreases. So
the block's mechanical energy.
Good. So the mechanical energy appears to decrease. Well, it does decrease, but because of the energy lost to friction, which you could calculate by finding the work done by friction, which would be mu times n times that distance traveled. All right. That's significantly better there. I also cut out a few, so that maybe.